Hello, today we'll start talking about access control. Access control is about who gets to access which resources and how they get to use them. In a multi-user system, you need to have some way to control which users have access to which resources. So for example, only root, the superuser account that administers the machine, should have edit access to the password file. The topic of access control encompasses both defining the policy, which users have which access rights to each resource, and also it's about how to enforce that policy once defined. Earlier, when we discussed the security policy primitives of confidentiality, integrity, and availability, we talked about unauthorized users. For example, confidentiality says that only authorized users should be able to read the protected data. With access control, we fill in the details of how to keep track of who is authorized and who is not, and one way to enforce those policies in an operating system. There are three main pieces to consider: who, which users have access; what, which resources are being protected by access control; and how, what type of access is allowed, for example, read, write, or execute access. We use the terminology subject to describe the entities needing access, object to describe the protected resource, and right or type for the type of access allowed. Subjects include users and processes. We often talk about a user, but often what we are really referring to is a process acting on behalf of a user. Objects are the resources that we are controlling access to. Objects include files, the logical structures that include records, files, directories, directory trees. Objects also include memory, so blocks, memory blocks, or pages of memory, segments of memory. Objects include I/O devices. These can be communication ports, system clocks, network nodes, the keyboard, the screen. And also objects include users and processes. All subjects are objects. That is, access to a process, for example, may be controlled. The process or user is a resource to be protected. The typical rights we talk about are read, write, and execute. Create is the right to create a new process. For example, it's another right. A transfer is the right to transfer your rights to another subject, for example. If you have read access and transfer access to an object, then you could grant some other user read access to that object too. There are other rights as well, and different systems may use a different set of rights. Read, write, and execute are pretty universal though. Before we get into the specifics of any particular access control mechanism, let's go over some best practice. These are properties that ideally all access control mechanisms should provide. The three main ones are universal application, least privilege, and type checking. We'll go through each one in turn. Universal application says that every single access should be checked. Whatever the current policy is, it should always be enforced. Policies can change over time, users' roles can change over time, and enforcement should keep a pace. As a real-world example, I have an old student ID. I should not be allowed to use it to gain access to student resources at my old campus. In this case, the policy has not changed. Students are allowed access, but my role has changed. I am no longer a student there. My card has an RFID tag, and there are readers on the doors of labs and classrooms at my old campus that allow or block access. Every time I want to enter a locked door, every access, I have to present my ID card. The set of RFID tags allowed to open the doors is kept up to date with the set of current students. Since I've already graduated, I can no longer use the card to enter locked labs and classrooms on campus. This is good. This is as it should be. But using the same student ID, I could try to get a student discount at the grocery store. They had that in California. And I can present my ID. The store doesn't have the appropriate RFID reader. The cashier will just be looking to see if the ID is a valid student ID and has my picture on it. In this case, the check was done once. When I was issued the ID, someone checked that I was in fact a student. And after that, people just check that I have the ID. It's a cached result. In practice, using cached results is a bad idea. But also in practice, we use cached results all the time. It's expensive to do a full check for every access of every resource. For example, when you open a file, you can open it in read mode or in read-write mode, for example, and at the time you open it, your checks, or the process running on your behalf, checks that you have the sufficient permissions to open and read or write the file. But every subsequent write to the file is not checked. If you had the permissions to write when you open the file, it is assumed you retain those permissions for the length of the time your process is running or the file stays open. And we saw how this can go bad when we talked about malicious software or vulnerable software. So we actually don't achieve the ideal very often of universal application of access control. And this is because, as always, there's a trade-off between security and usability. Something that introduces too much overhead just won't get used at all. There are some substitutes for universal application, and these include random checking. This is where you randomly select a subset of all accesses to check. It is more efficient than checking every single access. Another policy is random auditing. So log all the accesses and then later randomly check some of those accesses. This allows for a greater number of checks because the check itself doesn't have to take up time at the point of access. However, this provides only detection of unauthorized accesses and not prevention. And then finally, there is selective checking. If a cheap-to-implement first glance seems suspicious, so you check every access but very quickly and cheaply and incompletely. But if that initial check produces, raises a flag, it looks like the access is suspicious, then do a more thorough check. Okay, going back to our best practices, the next one is to follow the idea of least privilege, which says that every subject should be granted the least amount of access necessary to do its job. This supports the idea of failing safe. Limiting the amount of privilege that a subject has limits the damage that can be done if a subject is compromised or turns out to be malicious. Adhering to least privilege can be difficult, though. It requires first knowing exactly what accesses each subject will need. And often designers overprivilege an entity, let's say a process, to ensure availability. No one wants their program to fail or crash because it doesn't have the resources it needs to do its job. We saw this play out in the early days of Android development. Android apps include a manifest that lists exactly which privileges the app will need. So for example, the app will need access to the camera or to the list of contacts. Developers new to Android would often get frustrated when their app didn't work as expected because it failed to include some obscure privilege. Searching for sample code on the web will often produce snippets of code with manifests that list all possible privileges, with the comments in the code that say, just request all the privileges so you know your app will work. This is a serious and dangerous failure of least privilege, and it's also an example of how people will work around security measures that get in the way of productivity. And then finally, type checking. Type checking says that operations should be meaningful for the object accessed. A type system, broadly speaking, defines the kinds of objects that will exist and the legal operations on those objects. We talk about type systems in programming languages most often. For example, in a strictly typed language, there might be integers and booleans. And addition is defined for the integers, while logical and logical not are defined for the booleans. ANDing two integers together is not defined and would not be allowed. We can use the same concept in a less formal setting. So for example, printers have been known to have vulnerabilities. In some cases, an attacker can send a well-crafted document to the printer that causes a buffer overflow within the printer's firmware or software, and allows the attacker to then execute code remotely. That printer may be connected to a local area network, and malicious code can start to probe and possibly gain entry to other machines on the network. Type checking in this context would mean ensuring that a printer, for example, is never logging into a server. Printers have a very well-defined role in a network. Any actions they take outside that role should be prohibited by the system. Having outlined some best practices, we now go into specific access control policies. There are 4 basic policies that tend to be in use. We will go over 4 of them quickly and then dig more deeply into the first 2. So the first is discretionary access control, or DAC. Access control decisions, these are access control decisions based on the identity of the requester, the resource, and a set of authorizations. It is called discretionary because the owners of a resource, say a file, get to decide who else has access to that resource. With mandatory access control decisions are based on the security clearance of a requester, the subject, and security classification of the resource, the object. It is mandatory because individual users do not get to make access decisions about resources. If I create a file under mandatory access control, I don't get to decide who else can read the file. This type of policy makes sense in high security environments. In role-based access control, with role-based access control decisions are based on the role of the requester within the organization and the rules governing what access is allowed to users in which roles. And finally, with attribute-based access control decisions are based on the attributes of the user, the requested resource, and the current environmental conditions. And this is gaining acceptance, this style of access control. It is flexible and it's capable of expressing complex and detailed access control policies. But there are some concerns about high overhead. Attribute-based access control has seen adoption in web services where the overhead is less noticeable. So for example, some of the subject attributes might be the subject's identity, the subject's organization, job title, or role. Some of the object attributes might be title, the date of the creation, or ownership. Environment attributes include current date and time, or the current threat level even. Note that these attributes are not fixed, and so access decisions are not fixed, but can change over time as the attributes change. Okay, let's discuss discretionary access control. We'll go over 3 mechanisms for implementing discretionary access control. These are 3 mechanisms that might be used by, say, an operating system for controlling access to the files and directories of the system. The first is an access control matrix. This data structure is a single table listing all the subjects and all the objects. Each entry in the matrix lists the access rights for the corresponding subject to object. The operating system or supervisor checks this matrix before allowing any access request. The matrix has some advantages. It is easy to understand and easy to implement, and it is also easy to revoke access if needed. If you want to revoke all access to an object, you just go down the corresponding column and rewrite the access rights. If you want to revoke all of a particular user's accesses, you just go across the row and rewrite the access rights. However, it also has a major disadvantage. The matrix itself is sparse. On a shared system, most files are accessible by only a single user, the author of the file. This makes the matrix an inefficient way to store access rights. The next mechanism we'll look at is an access control directory. Here, each user or subject has a directory pointing to their accessible objects and the associated access rights. This data structure is easy to implement and does not have the inefficiencies of the matrix. On the other hand, some users' directories can be very long, and files that are shared across many users are listed many times, once in each user's directory. This is inefficient. It's also the case that a single file may be listed by different names, both within a single user's directory and across different users' directories. In the former case, where a single user's directory has the same file listed twice but under different names, this leads to ambiguous access rights. In the latter case, where 2 different users have the same file listed but under 2 different names, it is difficult to assess which files are shared and which are not. And finally, revocation is more difficult with an access control directory compared to with an access control matrix. With the directory, revoking all access to a single file requires searching through every list to find all users with access to that file. Finally, we have an access control list. Here, there is a main directory with one entry for each file. Each entry points to an access list for that file. Each access list is equivalent to one column of the access control matrix. There is one access list per object. The access list lists each subject with access to that object and that subject's access rights. This data structure has a number of advantages. It allows for the implementation of default rights efficiently. Users not listed in an object's list get the default right. For example, that might be read access for public files. For public or widely shared files, for example, think of the C libraries, this is much more efficient than having to explicitly specify read access to every user. Because each object only appears once in the main directory, there's no issue with aliasing causing ambiguous rights, and if two users both have access to a particular file, that will be obvious from the file's access list. Finally, revoking all users' access to a file is easy. Just update the file's access list. Revoking all of a user's access is still cumbersome. All access lists must be searched to find every place that user is listed. We'll end with a recap of the benefits and drawbacks of each scheme. The access control matrix is easy to implement and understand. Revocation of both a file's users and a user's rights is easy, and there's no issue of aliasing to worry about. However, it's an inefficient way to store access rights. An access control directory is also easy to understand, and it fixes the sparse matrix problem. However, it makes revoking all access to a file difficult. It is subject to aliasing confusion, and there can be long lists when every publicly shared file has to be listed for every user. Finally, an access control list is efficient. It makes it easy to revoke all access to a file. It does not suffer from aliasing issues, and it allows for default rights to be used efficiently. However, it is more work to revoke all of a user's rights. Every list must be traversed. We'll end here.